Also, you can ask all questions during the lecture. Completely fine. Okay. So, as Lena asked, and that was also my plan. Let's estimate this I integral asymptotically and show that we have a normal wave structure, a normal diffraction wave structure. So what do we want to have? We want to have some cylindrical wave going here. We want to have some plane wave going here, and if we like very smart, we also want to have a penumbra. Do you know what is penumbra? It's like a shadowy region. It's like a half shadow region. So when you hear, you just are in the shadow. You only have diffracted field. But here you have penumbra, and you can have some interference pattern. And this thing was described by Fresnel, I think, and Carnot. Diffraction by a knife edge when he had some interference lines afterwards. And so, do you recognize this integral? Do you know a special function that can be used to express this integral? So we cannot compute it in terms of simple functions, elementary functions, but it is we can express it in terms of a special function. So let's write this function down. Let's choose a variable. Like this. And then we have the following expression. Fine. Okay, maybe you recognize this function. Never seen before. It's known by two names. A version when we don't have an I is called error function. And a version when we have I is called Fresnel I integral. Complex Fresnel I integral. It's like, for real we will have like sine and cosine of a squared argument. So this is complex Fresnel. Oh, how do you call him? Fresnel or Fresnel? Is he Fresnel? Because he's Fresnel. So you just don't know the guy.
I think he's
Fresnel.
But in Spanish we say Fresnel.
You say Fresnel. I mean, I know how his name is spelled. It's like this.
Spelled like Fresnel.
But in Russian we say Fresnel.
Is it French?
Because he is French, maybe he is like, I mean, I will not point fingers, but these people, they skip some letters.
Fresnel.
So, anyway, what's important thing? So, notice when y is positive, we have a stationary point. which is 0. So d over dt squared will be t, which is stationary when t is 0. And when y is negative, then we don't have a stationary point. So stationary point tau equal to 0. Okay. And this is probably everything that we should know to write down this integers. And when y is, for example, just negative, then we can apply integration by parts, because actually value of this integral is exponentially small, and the series we will get from the integration by parts will be converging because of the exponentials. I will, if I have time, I will do it later. But right now I just give you the result. And also you should know it from your second year at university. It's approximate. And here we have don't have, and it's the same. I forgot. Which is what we expect, because we only have a plane wave in the upper half plane, like, so it's nice. We have the incident wave only in the upper half plane, and then we have only diffracted wave in the lower half. And also you can look at the structure of the diffracted wave. It looks like almost like a Green's function multiplied by some what I would have called a directivity of the scattered field. So this thing behaves as a cylindrical wave because it's a Green's function. Green's function behaves as a cylindrical wave. It's like a bit non-standard, but we have this y in the denominator. Okay. So you can take and compare this solution with the exact solution we applied at the last lecture and the lecture before, and this solution will match somewhere here. Maybe it's slightly bigger, like this here. So here the agreement will be quite nice. And generally, you like it's not linear, so it's some parabolic region. But if you have your angle, so your angle of observation is kind of satisfies approximately this property. So it's more or less fine to use parabolic approximation. That's what many applied people do, especially when they study like complicated waves. And this is, when you have, what is a good example? You have theta equal to pi over 4. So it's almost pi over 4, the value of sine. So it's 1 over 2. It's more or less the same thing. Is it pi? No, pi over 6. Yeah, pi over 5 is worse. But pi over 6 is the same thing as 1 over 2. Because it's 3 divided by 6. So we know sine pi over 3 and pi over 6 is almost equal to pi over 6, which equal 3 by 6. Some engineering stuff. So it works fine. Okay, and we have a structure we expect. The incident field and diffraction field. So let's continue. But now I say, okay, what happens if our plane is parallel? So now I say consider the diffraction over parallel plane. What do you think will be the solution? So first of all, the solution will be symmetrical. Second, we again know all the boundary data. We know the boundary data here, and it's also just one. But now you know, since we have only propagation here, so wave from here, it cannot come here. So there is no way it can get there because it's only propagates on the right. And basically, my solution is very similar. It's like, so it's the same function, but now because the solution is symmetrical, I just put this thing. And here, so on the upper half plane, I take also just half line or integral, and then on the lower half plane, I take just the reflected integral. Because it's symmetrical, I only can find solution in the upper half. And that's it. That's how I get a symmetrical solution, and only this asymptotic I will use. And that also makes sense because now I have the incident wave everywhere. I don't have any shadow. It's everywhere. Interesting. You want you can write it down. Okay, well, just to stress, I will put a frame around it. So this is a solution for perpendicular frame. Yeah. Not perpendicular. Let's go lateral. Half plane. The synthetics.
Can you get, so as you said, we can only get information to the right.
From the left to right.
From left to right. So that means that we cannot get information from if there's diffraction. But there's no propagating in that way.
I mean, what I had, like, I can be here I again can use symmetrization if you like. or I can, if you're like worried about this explanation, I can put an artificial boundary and put like Neumann conditions here. But since there is no scattered field, it's just 0. And then I like, I only integrate on half plane. And this and diffraction field propagates from left, so I have diffraction field. That's fine, it just stays on the upper half plane. And it works the same way. It works actually for Greenwald's equation. It's also like kind of doesn't care about lower half planes. Like each half plane, you can say, but it's like a philosophical part. You can say they exist separately because I have a symmetry. If I know solution at once, one half plane I know in other. Or maybe you can say they are connected. So that's it. But yeah, you can formalize it like this. Or like another way, you can apply method of reflections and then apply integration on to sheeted surface. And then when you do the symmetrization, corresponding part will cancel each other. That's nothing stops you to consider it to sheeted surface.
But you scattered field on the like left from your initial line is 0.
Yes, yes, scattered field is 0. And that's, almost true. When you have a high frequency wave, you have almost 0 backscattering. So it's okay. So that's like a physically reasonable behavior. So, okay, I have a small loop. So we can introduce a scattered field as for this problem like this. Oh, that's bad. I deleted this part. But you can believe, so where I define theta actually is not theta, it's tangents of, use weird language, real theta. Real in terms like just an angle. Real. So it's a correct way, like a formal definition for theta is like this. So if I introduce my theta as a tangent of angle of observation, just y divided by L. So I have y. This is like real theta, but I almost use them interchangeably because I want this property to be almost satisfied. And if I define my theta like this, S over theta will be equal to theta. You can, when I was writing this lecture, I was a bit concerned that I'm getting imaginary I, but maybe like one of the volunteers can check that this solution is close to the Greenwald solution, and maybe this I should live in the definition of the Green's function. So we have some constant here. So maybe two constants for Greenwalds and parabolic Green's functions are just different. But anyway, we have a structure of diffracted field we expect. We have this part that only depends on the angle of observation. And here it's just a tangent of the angle of observation. Okay? Okay. So directivity. Formal definition. So, like for any problem, especially with compact scatterers, we can define the directivity as follows. In a fashion where theta, as I said, is y over x. So then I want to prove the following relation. So let scattered field be known on some line. And then I can say I want to prove that from scattered field known on some line I can obtain my directivity as a Fourier transform of the scattered field. Let's show it. How would we show it? What your idea? Of course, we will use which formula we will use to find the expression for the directivity. We will use propagator. I only show you one formula to that's like the Lord of the Rings. One formula would rule them all. Okay. I will do some algebra. So the propagator formula says I'm writing the same thing, just writing down the exact expression, explicit expression for its function. So the derivation is quite simple. So then I compute the square to the face term. Write down it explicitly and take a limit. Maybe a conceptual part is to take a limit. But it's all very simple algebra. Two terms are left from our quadratic expression. Then I say, okay, let's now x and y tend to infinity, but in such a way that theta equal y over x is constant. So this term is constant, but this term tends to 0. And probably you might have recognized this thing. This thing is a Green's function. This is gxy, and we have what we wanted to have. We have gxy multiplied by this bit then as theta. And okay, let me finish. As theta equal to so now you can use, so it's a Fourier transform, which is cool. Now you can use this knowledge to compare the solution of parabolic equation, like all the solutions we obtained with solution of Green's equations. And we actually finish it quite soon. So I have a homework problem. It's a theoretic. So this idea of solving of diffraction by a strip can be extended to a problem which is very complicated for Green's equation, to diffraction by a half plane, so to a problem of diffraction by a strip. So suppose we have a strip, again we have some field distribution u equal 1, and what we want to find is field distribution on this line. And let the strip be of size A. This is line OLY. So how do we approach such a problem? Right. So what do? We can solve this problem in two steps. First, we apply a propagation formula from here to here. Write it approximately like this. And then, so we will obtain some field here. And once we know this field, we can apply propagation formula for the second one to here. So right away we can express a solution as some double or integral. And if you do a bit of research, you will find out that there is no simple analytic expression for Green's equation. Solution is quite mathematically complicated. So formally, I can summarize this idea in quantum mechanic terms. In quantum mechanic terms, I will say that U Ly is given by double propagator from U 0 Ly. This is some quadrature. Those who are lazy to do it can find one of my papers where I did it. This is a paper by me, my former boss. So we did it together. Vertical journal in 2016. It was 3 years ago. But if you're curious, well, you can do it yourself. It's quite simple. But we did a bit more than this. But also I showed that you can express the solution in terms of Fresnel or integrals, so you can get rid of double quadratures, only a single quadrature. Okay, that's it, and we have a bonus part. I will show you how to obtain asymptotics and bonus. And you should know it already. Asymptotic by integration by parts. But if you skip this bit, so what we have? Fresnel integral. Constant. As a usual trick, I will multiply it by 280 and then divide it by 8 tower. So this bit I can then refer as div and this bit as div. And then v will be just an exponent. Usually. That's so here we don't make any approximation so far, we just integrate. So we get an equivalent expression. And here I think that my zeta is positive, because if it was negative, then I would have had problems at 0. So I wouldn't have a convergent or integral. That's the point where we have a saddle point. That's why we have this one. So I can always subtract this saddle point contribution. But of course this thing decays much faster than this, not much faster, polynomially faster than the previous one. And thus I can write something like this. Two. That's asymptotic. But it shouldn't surprise you. I think that's it. Any questions?
So if you were to, let's say that the case of your strip, perpendicular, it would just be like same solution but splitting.
Yeah. Yeah.
Does it mean that we can only consider the problem of half plane when it's perpendicular or parallel? It can be angle.
I mean, it can be whatever you want, but for parabolic equation it doesn't match. You can do the angle, but then you have to,
Then this consider
yeah, your integration will be more complicated. So your regions will vary. It's just like the best when you have an angle. So your plane located like this. Smart people do the following things. They choose local coordinates that go along the surface of your scattering. And then you always have the same parabolic equation. But yeah, if you had your strip like this, so you would have had two integrals, this one and this one. But here you would have had some shift, and you would have had like this Fresnel bit, which you produce. So you will have some Fresnel bit here and Fresnel bit here. So basically you have a sum of two plane wave solutions shifting, which is like a first order terms of geometric series, geometric diffraction series, or just a sum of diffraction by terms. Parabolic equation is that simple. But then you have something more complicated because you integrate with them, so they kind of. Okay. Okay. Thanks for listening to me. Don't forget to like, share, subscribe, and hit the bell.